Hi, this is Mr. Swanson here, and we're going to go through our fourth lesson on chemical reactions called double replacement reactions. So follow along with us and continue to try some of the practice problems, and make sure you have your reference sheet as well, because you're going to probably need to go back and forth to the reference sheet as well. All right, on this slide you see two examples of some double replacement reactions, some cartoon examples as well as real chemical reactions. But on this left you see that we have two people, and you might not notice this right away, so here's your reactants. They have this person with a red beard, like Mr. Kuhn and Mr. Swanson, with a black hat, and then a green beard with a white hat, and so they end up switching, okay? So the hats ended up switching. Now you could say the hats ended up switching, or the people ended up switching, but either way, there was a double switch. Same thing here with the bunny and the meat, and then the dog and the carrot. The food switches or the animals switch, but either way there was a double switch in this example. So the same thing that is going to happen down below, and you're going to get new compounds formed. And an easy way to tell that this is a double replacement reaction is you're going to see a metal and a non-metal plus a metal and a non-metal. I guess you could say that as a cation and an anion. That might be more correct, but and they're going to switch, the metals are going to switch, or the non-metals are going to switch. So you can see that these are going to be a double replacement reactions where you're going to have those metals switching up. So here's what those reactions look like when they are completed, and we like to say that the metals switch places, but you could also say that the non-metals switch places, just like in the hat example up above. And so we're going to talk about how to, write exactly the new products that are formed, and how to predict when this is going to happen and when it's not going to happen. Now, not every time that you have two compounds is a double replacement reaction going to happen. There's a couple conditions that need to happen in order to make it happen. And, we say a precipitate, so some kind of solid forms, or a gas forms, or water forms. And if one of those three happens, the reaction is going to, go forward. But if one of those is not happening, then we say the reaction does not occur. And so we're going to have to pay attention to see if one of these three things happens. I will link this video in Schoology to look at. There's kind of some beautiful double replacement reactions happening. By now, hopefully you're familiar with the word aqueous, and that's really important in double replacement reactions. And in reactions in general, usually the compounds have to be aqueous or liquid to make them happen. Solids don't really react with other solids very easily. So we're going to take a look into aqueous solution and what that really means and what's happening on a molecular level. So an aqueous solution is one that is dissolved in water. So the compound is somewhat dissolved in water. And this is really going to be happening with ionic compounds that are dissolved in water. And when we say dissolved, that means separating into its anion and cation. So when NaCl, which is an ionic compound, separates, it's going to separate into sodium, and we know sodium has a +1 charge, and chlorine with a -1 charge. Just like that, Ca, calcium phosphate, is going to separate into calcium ions and phosphate ions, and in that water there's going to be 3 calcium for every 2 phosphate, and that's what these coefficients are telling you. Subscripts are telling you at the bottom, that for every 3 calcium ions that dissolve, there's going to be 2 phosphate ions, and you're going to see that the charges would balance. So it's important conceptually that you understand what aqueous means and what a picture of an aqueous solution would look like. And so if we take a look at KBr right here, you're going to have KBr, which says it's aqueous, so we'll tell you if it can dissolve in water. And that means that there's going to be a 1-to-1 ratio, so every 1 potassium, there's going to be 1 bromine, 1 potassium, 1 bromine, 1 potassium, 1 bromine, 1 potassium, 1 bromine. And so you can see that in the solution. Same thing over here for sodium chloride, 1 Na, 1 Cl, 1 Na, 1 Cl, and so that 1-to-1 ratio. So if we took those two things and mixed them up, again, you're going to have that 1-to-1 ratio of just these ions floating around. So make sure you're able to draw a solution or draw what it looks like to have the ions of a molecule be separated. The last slide it showed that there are going to be the ions broken up, but now we are going to add water into the mix. And so you can see here that the water molecules, remember, they have dipoles, right? The oxygen is going to have a partial negative charge, the hydrogen is going to have a partial positive charge. And so when they are floating around, when an ion is floating around in water, since chlorine is a negative charge, the hydrogens are going to be the one, because hydrogens are partially positive, that kind of surround the chlorine. So all the hydrogens are going to be surrounding the chlorine, and the oxygens are going to be on the outside. Now, if we look at that and compared, so like, the negative of a chlorine and then the positive of sodium, well, oxygen has a partial negative charge, and so that's going to be attracted to the oxygen. So this time the hydrogens are going to be in the outside of this molecule. And so what to be dissolved in water means is water molecules completely surround the molecule, and the orientation of the water molecule is going to depend on what type of ion you are dissolving. And then eventually, when you run out of water molecules to surround an ion, no more of that ion can be dissolved in that solution. So here's an example problem of silver nitrate and sodium chloride being mixed together. And when you do that, again, the Ag and the Na switch places, and they make silver chloride and sodium nitrate. I hope I said silver chloride. Anyways, the point is, we care a lot about what state of matter they're going to be after the reaction takes place, because again, this is only going to happen if at least one thing is solid. In this case, it's silver chloride. Now, how do I know this is solid? How do I know the sodium nitrate is aqueous? Well, we have to, there are some set of rules that you can memorize, but we in this class are just going to ask you to consult a chart, and it's called the solubility chart. And so we're going to explain kind of how to look at that. So keep silver chloride and sodium nitrate in your mind as we look into the solubility chart. As we look into the solubility chart, the word soluble means it's going to dissolve in water, so soluble and aqueous, same thing. And if we say it's insoluble or not soluble, that means it's not aqueous. Or another word to say that is a solid. Okay, so those are going to be the two main conditions. Solubility charts and tables come in all shapes and sizes, and we're going to show you a couple different versions over the course of this unit. Here's a very common one that you might see. And so you are taking a look at some metals, okay? So let's look at maybe some alkali metals, and what is their solubility, and it says generally they're soluble. In this case, they're always soluble, and there's no exceptions. And here's some examples. But here's another one, sulfates down here. Okay, if something contains a sulfate, it's probably going to be soluble. That's your best guess. Except when you mix it with these, then it's going to be insoluble. And again, there's some more examples. So you want to read this chart, and you're going to say that, hydroxides are going to be mostly insoluble, so they're not going to be soluble, except when they're with like lithium, so that would be an alkali metal. So if it's normally insoluble, but lithium's an exceptional, then lithium hydroxide is going to be soluble. Hopefully that makes sense. So just pay attention to the solubility and then the exceptions to that rule. And so we're going to practice that many times. So take a second to look at these examples and write out the formula, and then look at the solubility chart to determine if it's soluble. If it is, write aqueous, AQ, and if it's insoluble, write solid. And then come back and check your answers. All right, so hopefully you got these answers, and I'll quickly go through them. Sulfates are almost always going to be soluble. Chlorides also are almost always going to be soluble. I don't like how I did this. But when they're with lead, they're solid. Same thing with carbonates. Carbonates are almost always insoluble. phosphates as well, but when they are with potassium, they're aqueous. So all you need to do is consult that chart at on the last page. Here are a couple just terms to remember what we mean, the difference between soluble and insoluble. I think we've gone over that. And then here are the different ways you are writing out the states of matter when we're looking at a chemical reaction. So you write this as a subscript 2, kind of right at the end of the compound. Let's look at another example about, kind of zooming in. What's it going to look like when we take this lead nitrate and Ki and mix them together and see what happens. Since both of these are aqueous, you can see that the ions are broken up into, or the compound is broken up into its ions in the correct ratio. And so, and this is kind of showing it's starting to break apart. And then here's the after. So after we mix them, they're going to come together. And if you look at this, they're just floating around, and it looks like some of the negatives are like right next to each other. Well, you have to think about depth, right? This is trying to show a 3D picture. But so they're all just floating around with each other right now. But here you can see that over time, that lead is bumping into the iodine. And when lead gets close enough, it's going to bind with iodine. And when it binds, it sticks. It doesn't unstick, right? In water, it doesn't unstick. It's what we call insoluble, or it forms a solid. And so this is the solid that is going to be in a solution of potassium and nitrate. So the potassium nitrate, again, they're aqueous, so they just stay floating in water, but the lead and the iodine come out of the water, we say, as a solid. And so they're going to end up floating to the bottom or staying kind of in solution, but they're going to form that solid. If you're doing this reaction in the lab, you would see some kind of solution, and it might not be clear, and I don't know what potassium nitrate looks like, but in this case, it is clear, but at the bottom, you can see that PBI. So that's an evidence of a solid. Some kind of, sometimes it's cloudy or milky, but a lot of times the solid actually, forms and goes to the bottom. Before we go on to another idea, let's just review quickly. So in this double replacement reaction, we're going to form 2 new ionic compounds. And this is the general format of this. So this is what you'd see for a double replacement. A represents just a cation, B represents an anion. Remember, the cation is always first. So A and C are the cations because cations are first. When they switch, remember, just switch either the metals or the nonmetals. I think it's easiest just to do the metals. And then when you're putting them back together, watch out your charges, okay? Remember, everything that comes together has to come together as a neutral compound. So you have to reform the compounds with the correct ratios. Check to see if the solubility rules say one is going to happen, to say if this is going to happen. And remember, for a double replacement reaction to happen, one is going to have to be a solid, and the other one is going to be an aqueous as well, okay? So pay attention to that to see if this reaction is going to happen. And then at the very end, you want to balance your chemical reaction. At this point, you're probably ready to try one on your own, so read through this problem and try to write out the chemical reaction and see if it's going to happen. Finish it up, predict the products, and then at the very end, balance it. And then once you're done, come back and check it with me. All right. Hopefully, you are able to get this answer, and the answer is yes. Yes, a precipitate will form, and yes, it's this one, because iron and hydroxide make a solid. So hydroxides, the OHs, are normally insoluble. There's a few exceptions, but iron is not an exception, so that makes it a solid. So the last thing we want to talk about is a net ionic equation. So after you do a double replacement reaction, it's best practice then to just show, or when it's asked for at least, is a net ionic equation. And so to do that, you're going to want to write the complete ionic equation first, and then you're going to cross out the ions that are common. And we do this to show really what's going on. So the full equation doesn't show, it shows more information than needed, and so you want to reduce it down to its net ionic equation. So how you do this is, and we're just using the equation above right here, you want to break the things into its ions. So we know Fe is a +3 charge, and we know there's 3 Cl minuses, and we know, and you want to write AQ, and then there's 3 Na pluses, and there's also 3 OH minuses, and that reacts to produce, and then FeOH is a solid, so we can just leave that, right? And then 3 Na pluses and 3 Cl minuses. And so, and you should probably write aqueous on all of those, but just for the sake of time right now, I'm not going to write those. Okay, so we can put it in the final answer. So now what you want to do is you want to go ahead and cross out the ions that are common on both sides. So I see chlorine on both sides, and I see sodium on both sides. And so we're going to cross those out. And so what we're going to do is write the final net ionic equation, which is going to be Fe plus 3 aqueous plus 3 OH minus aqueous reacts to form FeOH3 solid. So the steps are essentially write out the balanced equation, break it up into ions, and then cross out the ones that are common on both sides. So for the rest of the slides, you're essentially practicing the same idea. Here's just kind of a nicer version than what I just showed you. Notice how they are writing the aqueous, and they should use parentheses for all of those. So maybe practice this one. I'll pause the video, and I'll write out the answer, and then you can come back and check yours. So this is what you should have gotten, and hopefully you did those in order. Kind of first wrote out the products and balanced it, second broke it up into ions, and finally crossed it out and figured out just what is going on in this chemical reaction. So for the next couple problems, you're going to do the same thing. So pause the video and try to practice another one. Okay, so hopefully at this point you see that both products that are going to form are going to be aqueous. And when you do that, this reaction is never going to happen. So instead of writing this, you just write NR, no reaction. Okay, because both products are going to be aqueous, nitrates are always aqueous, and carbonates are aqueous when they're with sodium, then you just write no reaction, and you're done. Okay, for this next problem, hopefully this is what you got when you tried it on your own as well. Notice that these charges, again, barium's a +2 and sulfate is a -2 at the bottom here, and so the charges are a 1-to-1 ratio. And it's probably best practice to put in the second level that each of these are aqueous, but just for the sake of making these notes shorter, I'm not. Okay, try one more, or try a couple more and see if you can get the correct answer. Okay, so hopefully when you tried the first one, you realize that it's the exact same net ionic equation as the last page, even though the chemical reaction was different. So you definitely, many reactions are going to have the same net ionic equation when their full written chemical equation are different. I also skipped the step, so I went right from the molecular equation to the net ionic, just because I can do that now. If you need to, definitely take that intermediate step. Okay, so what's best is to try some of the problems from the unit packet, so the section on double replacement, and remember, if both products are aqueous, then you write an R. No reaction. Okay, good luck.